Thank you for coming, and thank you for getting up so early for me. I'm Arno, I'm from ThinkCell, and we are going to talk about ranges. Now, to gauge a little bit who you are and how much you know about ranges, let me ask you a few questions in the beginning. Who knows boost range? Okay, quite a few of you. Who knows Eric Niebler's library, the range v3 library? Also quite a few. And who already uses ranges in everyday programming? Okay, fewer. All right, so why do you want to use ranges in everyday programming? You really should. I mean, usually when you have your regular STL stuff, right, you have something like this. You have a vector, and then you call sort, and you have to call vector begin and vector end. And then you want to throw away duplicate elements, and you do this with standard unique, and you plug in the begin and the end, and then you erase, and again, you plug in the vector and the vector.end. And I mean, how many times do you really want to mention the vec and the begin and the end? And it's all quite impractical. What you really want to do, I mean, pairs of iterators, they belong together, right? They're describing really one thing. And you want to put this pair of iterators together in one object. So then you get something like this, much nicer, right? You sort the vector, and then you throw away the duplicate elements. Only I mentioned vector once, and the result of the sort goes into the unique in place, and everything is good. Now, why do I think that I know something about ranges? Well, ThinkCell has a range library, and our code uses ranges everywhere. We have about 1 million lines of production code. And along with that production code, which has been there for about 12 years now, we evolved the range library. And we were free to change, because it was all in one company, we were free to change the library and the code. And whenever we found that some concept didn't work, we were able to change it. And that's luxury, because usually when you have a library that's used a lot, you can't just change it around, because then everyone who's using the library is going to complain. Well, this was all one company. I was the boss, and so the code got changed. And that, I think, taught us quite a bit about how a good range library should look like. Now, we already have ranges in C++11. We have the range-based for loop. Probably everyone knows the range-based for loop. And then we also have some universal access to begin and end. You need this because, well, an array doesn't have any begin and end members, so you need some sort of universal way to access the begin and end. And then we also have, oh no, that's it, sorry. Don't have anything more in C++11. But the future is bright. Eric Niebler's pet project is to put ranges into the standard library, and that's certainly very welcome. That's long overdue. There is now a ranges TS, that's a technical specification that has been agreed on by the committee. It contains a lot of definitions, a lot of fundamental stuff that's not immediately applicable, but also it extends all the algorithms that are currently in the algorithm header to support ranges. So a typical implementation would look something like this. You have a find that takes a pretty much unconstrained template parameter. That's a range. And it calls ranges begin, ranges end to get the iterators and passes it on to the standard implementation that is still iterator-based. And you get back an iterator. Eric also has on the web the range v3. And that's his vision of how he wants the future standard to be. And that contains a whole lot more things. And in the process of this talk, I will compare his approach to our approach, the pros and cons. And so you will understand basically what the design decisions are that we may want to do in the standard going forward. All right. First of all, what are ranges? What can we use as ranges? Well, the first thing that comes into mind are the old containers, right? Vector list and so on. They have a begin and have an end, and you can iterate over them. They also own the elements that are in the container, and whenever you copy the container, you copy all the elements. And when the container is const, you can't change its elements. This seems all quite natural until we really start looking at views. Well, views, that's some newfangled thing, and the big world of ranges divides itself into containers and views. Not really. I mean, you know views. Views are your iterator pairs. Here is basically the simplest view you can come up with. It just contains two iterators. It has a begin and it has an end. And whenever you call begin, it passes out the begin, and with end, it passes out the end. And of course, just like iterator pairs, it references the elements. It doesn't own them. So there must be some container that the iterator range, or that view in general, is pointing to. When you copy the iterator range, or the view in general, it copies the object, it copies the references, but it doesn't copy the elements. You also have shallow constness, meaning that when that object is const, the iterators that are coming out of this object may or may not be able to mutate the elements, but that's independent of the constness of the view object. Now, iterator pairs are pretty boring. We want to do something a bit more exciting with the iterator pairs. If it would be just iterator pairs, it wouldn't be quite so useful. And the most useful thing you can really do with these views are to use them as range adapters. So here's the problem. You have ranges find. And that find finds in a vector of ints the first element that is 4. Great. Now you want to do the same thing with the int being packaged into a struct. You have a struct that has a field ID, and you have a vector of a's of that struct. And now you want to find the struct that has ID equals 4. Now, the problem is you have to do this in a completely different way than you did it before. Before, there was a function that says, OK, give me out of that sequence the first one that equals 4. Here, you have to use a completely different function. We don't use find, you use findIf. Now we have to write this equality here by hand. It's not nice. The semantics of these two things are quite similar, but we have to write it down completely differently. It would be much nicer if we could write something like this. Okay? We still have the same function that we used up here, range find, and we have this TC transform. That does nothing else but taking the vector and turning it into a new range of ints by extracting out of this A the ID field. It basically just executes this functor for each A, and that's then the range that it passes out. So what's important here is the transformation happens lazily. When you're creating this object, when I'm calling transform, nothing really happens. Just this object gets created, this wrapper object. And when I then start iterating over this wrapper object and use it as a range, then it starts applying the functor and creating the ints. Now, how do we implement such a thing? Oh, first of all, let me talk about, just to make sure that you understand how this works. When I'm writing this, ranges find with the transform, what is it pointing to? Well, we plugged a range of ints into the find, so the range of ints, when you plug it into the find, will return an iterator that points to ints, right? So, of course, this will no longer be a vector iterator. This will be an iterator of our view that is creating the ints, but it will point to ints. Now, it is very likely that at some point you will want to get an iterator out of the underlying structure that you have been modifying with that transform. How do you do that? Well, you simply add a .base. So that iterator that's coming out of this transform iterator is actually supporting a function .base, and it will return an iterator, the underlying iterator. This will be an iterator into the vector, and it will point to your A structures. Yes?
In this example, the iterator is dangling, right, to a range that no longer exists. Because you create that as temporary.
Where is the top one? The top one will be an iterator that is dangling. Yes, will be. Correct. Here, everything's fine. I don't use that one very often. Usually, you use this one, right? And here, it's fine because, yes, the iterator exists, but the .base here is then the base iterator, and that will be OK. That will no longer be dangling. It will point to the V. OK, how do we implement such a thing? Hold on a second. Well, not necessarily. It won't necessarily dangle. It won't dangle on the boost range library. It will dangle on our library and range v3. It depends on how you define the iterator lifetime. And we'll get to that. But it won't, with boost range, it won't dangle. Iterators are basically self-sufficient. Okay, here's how we implement this thing. And this is actually the implementation where it won't dangle. You have a transform range. Okay, this is the transform object. It contains iterators. And every one of these iterators contains the functor that it applies and the underlying iterator. So that's the vector iterator, and that's the functor that it will apply, the std memphen. And whenever you are dereferencing the iterator, it just dereferences the underlying iterator and pipes its result through the functor and returns it. The base simply returns the base iterator. So here you can see it won't dangle. Now, we can do the same thing with filters. So say you have a range of A's, and you want to return the A's that have ID equals 4. You would do it this way. There's another adapter, filter, that takes the vector, and you can here put in a condition that says, okay, which ones of these do you want? And keep in mind, this is again lazy. When you create this thing, nothing happens. When I start iterating, while it's iterating, it's starting to filter and skipping elements, and it's only returning the elements that pass the filter. Here's the implementation of this thing. You have a functor, and you have the iterator that we are currently at in the underlying range. And we also need the end, unfortunately. Why do we need the end? Well, when you have a filter, and the filter starts skipping elements, it could be that when you're at a particular position, it will skip all the elements until the end. And if you don't know where your end is, you're going to run off the end. So you have to store the end in addition to the iterator where you're currently at. And with this implementation, you would store this all in the iterator, and boost range does that. Now, how does the iterator look like? Of filter, of filter, of filter. Looks like this. Uh-oh. First, when I posted it to the mailing group, they didn't quite believe it, but yep. So, of course, you have the functor, and you have two iterators. Well, these iterators are again filter iterators. So they have a functor and two iterators. And the iterator has a functor and two iterators, and so on. So you get this combinatorial, this exponential growth of your iterators, and at some point you're copying around 10, 24 bytes large iterators while you're going through your loop. And this can't be very good for performance. What do we need to do? We must keep the iterator small. And the idea is, let the adapter object carry everything around that is common for all the iterators. So all the common information, that's the functor and the end, we store it in the adapter. And the iterator merely points at this adapter object and carries around its own position, its own iterator where it's currently at in the underlying sequence. And of course, that has the consequence of limiting the iterator lifetime to the lifetime of the range. That's actually the state of the art in range v3. This is how they do it. And then the iterator looks like this. Filter, filter, filter is a range and an iterator. And the iterator, the underlying iterator, has a range and an iterator and the range and an iterator. That's still not insanely great. We still have linear growth in the size of the iterators. And we want to stack these things. In reality, they become pretty big. You want to stack them at any arbitrary depth, and you don't want to pay a big penalty for them. So we weren't happy at things, though. We thought, okay, we need to do a little bit better. How can we do better? Well, we have to change our view of iterators a little bit. Okay, we're going to introduce a new concept called index. And the idea is relatively simple. The iterator is self-sufficient. It can always, when I say decrement, it decrements. When I say increment, it increments. When I say dereference, it can dereference. The iterator by itself. Now, I want to have a concept where, in addition to that iterator that I now call index, I will always pass in the range. So you no longer have to hold a pointer to the range. I will give you the range whenever you do the operation on the index. And one way to implement this is to say, okay, I'm going to implement the operations on my range object. So there's now going to be a function begin index that passes out the begin, the index corresponding to begin, same with end. And when you increment, you just pass in the index, and then the implementation of increment index has the range and the index together. Now, this looks something like, do we have an implementation? Okay, I do. I'll show you an implementation in a second. First of all, that's all great, right? But the world doesn't run on indices. This is some newfangled thing that ThinkStyle came up, and I don't think that the world is going to be like, yeah, that is so great, and now we change all our code. It's not going to happen. We need some compatibility with iterators, right? Because iterators are what STL has and what we always had, and so we need to stay compatible with them. So let's see whether we can do that. Well, it's actually not that hard. Iterators can do strictly more than indices. They don't need the range. So you can essentially, whenever you have an iterator, you can call it an index, and you're done. And then all the index operations are just the same as the iterator operations. The other way around is a little bit more involved, but not only a little bit. You have, when you go from iterator, when you want the iterator from an index, you can wrap the index in this wrapper. And that's completely generic. It'll look the same anytime. You have the index, you store the index in your object, and you also store a pointer to the underlying range. Now you have all the ingredients that you need, and you can then implement something like the increment by asking the range, please range, can you increment my index? Thank you very much, and that's it. Okay. So this is not really a problem, and our code base still uses iterators everywhere. Just for compatibility reason, I haven't changed anything to indices. Just under the hood, these adapters use indices. Now, how does this look like? Why can you be so much more efficient with indices than you can be with iterators? Let's take a look. The filter range still will store the functor, and I have it here as the example of the filter. The filter will still store the functor, and now a reference to its underlying range, so that the one that it is filtering. And to increment, the question is, what's the index type of this filter range? Well, it turns out that, and that's really the key, that the index type of a filter can be the same type as the underlying index. And the only way to see this is whether you can implement all the operations. So we can try with the increment, okay? So when you get the increment, you're supposed to increment your index. You're getting your index type in, which is your base range's index. You ask your base to increment that index, and obviously this type here is the same one that the base uses. You do this until you hit the end of your base, or until your functor, that's the dereferenced value pass, and to get it, you again call the base together with the index. So you can implement this operation using an index that is no more complex than the base range index. And this holds true for the filter, but it holds true for many, many other adapters as well. If you have a unique adapter, if you have a transform adapter, the story is pretty much always the same. You can always use the same type as the base range. It kind of makes sense, right? What you really need is, where am I in my original sequence? That's all really that matters. And when you do this and you stack these things in many, with a huge stacking depth, then still, because you are always using the same type as your base, you will go all the way back to the container. So in reality, if you have this huge stack of transform and filter and unique and whatever, then your index is going to be the iterator of the underlying container. So if you filter a vector, it's going to be a vector iterator. And now this makes the whole thing very efficient. Now you have a filter range. The filter range stores the functor and a reference to the base. It uses the same index as the base. You have its iterator is such an iterator for index, such wrapper thing, which really is just a pointer to the filter range plus the underlying index. So now all iterators are 2 pointers, no matter how big a stack you build. That's great. Okay, let's move on to something else. Range v3 and ThinkCell behave differently with respect to R values. R values are these things that are, for example, returned by value from a function. So if a function returns something by value, this thing will go away. It hasn't been assigned a variable. And that's an R value in a nutshell. Now, this is the regular situation, okay? You have an input that's a vector, and this vector is a regular vector that has a name. You declared it somewhere else, and you have a name for it, and it's a variable, and you just plug it into the view filter. What's view filter doing? View filter is producing a view. That means it doesn't own anything of that vector. It's just merely pointing at this vector. And it has all the properties that you expect from a view. It's a reference to the vector. It has O of one copy, shallow constantness, and so on. All the things that you have from a view. Well, now let's say we have this, okay? We are creating a vector. And we're creating the vector and directly put it into the filter. Now, imagine now the filter would hold a reference to this thing. Well, by the time the semicolon comes around and you are here and you're going through your range, that vector would be gone. And the filter would actually point to something that is no longer there. It would have a dangling reference, and the whole thing would blow up. So, what did they do? They said, this is illegal. It doesn't compile. When you have a view filter, this is supposed to produce a view, okay? Something that references the underlying elements. In the case of an R value, it can't do that. So what do? We don't compile. Okay, so imagine the user sees this, right? And you just type something and you say, oh, the vector, we don't have a variable for it anymore. We're going to inline it, no problem. It should work, right? And so, it doesn't compile anymore. Why? Well, let me try something else, okay? Let's do this. Actions are the thing that is in range v3 that is doing things immediately. This would actually take the vector and filter it according to the predicate, put this into the range. This will compile. That's all fine. Then you can put it into your any-off and all is good. Except this is a big trap. This is not lazy anymore. Suddenly the programmer, the innocent programmer who tried to make his code compile, will suddenly get something that behaves completely differently from what he had before. He made it compile and broke it in the process. Okay? Now I think this is a big problem. I don't want this to happen. I didn't want this to happen when I wrote our library. So what do we do? Now, ThinkCell works differently. If the adapter input is an L-value container, our TC filter, and that's our function now, not range v3, creates a view, and the view is a reference, and you get O of one copy and shallow constants and so on, just like what you would get with range v3 with Eric's library. Same behavior. But what do we do if the adapter input is an R-value container? So it will go away. We actually aggregate the container. The filter will no longer create a view. It will create a container that aggregates, has as a member the R-value container that you passed in. It's holding on to the elements. And because it is holding on to the elements, it has all the properties of a container. There's no real way around it. If you copy this thing, it'll copy the elements. But it will still be lazy. So when you start iterating over it, it will still filter the underlying container. It will hold first all the elements, which is pretty cheap because you got this as an R value. You can steal all the resources. You just have to move this into yourself, essentially. And when you then iterate over it, it will actually execute the filter. So the laziness is preserved. And what I think is important here is, and what I think they missed in range v3, what they really were afraid of in range v3 is that you have one name, call it TC filter, that produces either a view or a container. Oh my God, this may confuse people because you get different behavior depending on what kind of input you put into this TC filter. This was the thing that they were afraid of, really. It wasn't in practice, in our 1 million lines of code, that wasn't a problem. Okay? I don't think people did not get confused over it. The other situation is much more frequent, that you are basically expecting laziness, but you don't get it. This was a much bigger problem. In any case, laziness and containerness are two different concepts. If you want to introduce 3 different versions of filter and call them differently, okay, maybe that's a good idea, maybe that's okay, but that's still, I would maintain, make laziness and containerness orthogonal. Allow containers that do lazy evaluation. Okay, so that's my take-home message. And I don't see any problem with using the same function name to produce the container and the view. Yes.
What is the benefit of having the laziness preserved at that point? So if you copy anything, why don't apply the filter at that point, which is where you do.
That's why you have ranges any off. It doesn't need all the elements. You never know which elements you're going to need. Maybe you don't need them all. Maybe you never have to iterate over all of them. Maybe you're just checking whether it's one element. Done.
But you're still making the copy, so you still hold them. So if the filtering itself is not that much more expensive than copying, why don't do the filtering instead of just holding?
No, the copy, we don't need to copy. That's the point. This is an R value. This is an R value, and it gets aggregated. Oh, where's our code? Here somewhere. So
you're saying because you move it instead
you
of
move
copying
it, yes.
But you could do that with you could do the same thing and just apply the filter non-lazily and still move it, right?
Right, but then you would have to. I mean, the moving is an O of 1 operation. You take the vector and you move it into yourself. That's O of 1. If I go and filter, that's going to be O of n.
Okay, so you're not actually moving each element, just the vector itself.
Right. Yes, that's the crucial part. You take the container as it is and you move the whole thing into yourself, and that is usually an O of 1 operation. Okay, that's what makes it cheap. And then if someone asks you, do you have one element? You say, yep, that's okay, and then we throw the whole thing away. And maybe that's all you need. Okay, let's move on. What else do we have? We want to really make the returns of algorithms a little more flexible. We have this find, and the find usually returns an iterator, right? What you found. And if you didn't find anything, it returns end. Okay, well, maybe you sometimes need something else. And maybe we can make it a little more flexible by supplying an extra template parameter. Say we supply this extra parameter pack here, and instead of just returning the it at this place, we actually call pack with it and the underlying range, or the range, the input range. And if we want to return end, we call pack singleton, and let pack singleton do its thing, and pack singleton just returns the end, and the pack, by default, just returns the it. And in our library, we call it like this: find, return, iterator, or end. Now you can do something like this. I just put in insert false. I say, I don't expect the find to return an end. If this thing returns an end, my program is broken. Okay, it shouldn't. And I know this as a programmer, and now I have a way to express it. I can also do this. I can say, okay, now I don't want the iterator out. I really want the range from the beginning of what I filter, or for what I run find on, up to the point where I found it. And I want the head of that position. And you can also specify that in your find parameter. This proved very useful. If you can, what I always find nice, if you can write things inline. If you can write one big expression. And there it really helps if you can say, hey, I don't want to mention end again. I want to say, hey, find, return head, or begin. I don't want to have the iterator out and then combine it with begin or with end. I can do it all in one expression and either combine it with end or begin or a gazillion other things that we also offer. It's same with the pack singleton. I mean, sometimes you could, for example, pass the value out packed inside an optional if you wanted. So you pass out none if you didn't find anything, and if you pass out the value packed inside an optional if you did find something. So these things are all possible. One thing, think about whether lower bound should ever call pack singleton. Lower bound returns an end. Should it call pack singleton? Anyway, let's move on. Generator ranges. This is now probably as far away from the traditional notion of ranges as we've gotten. Often you have a function, an enumeration function, where you plug in a functor, and the function enumerates into this functor all the elements that it has. And for example, here you have GUI widgets, and you're calling traverse widgets, and you can have a window, and then the window is asked to traverse its widgets, and we have a button in a list box, and the other window is also supposed to list its widgets. And so you're calling this traverse widgets, and it's working through this complicated structure, and is plugging the elements into the functor. It's a little bit like a range, right? Because you're getting elements, but it doesn't have any iterators. You could try to write an iterator that does it, that goes through the widgets, but would it be a big pain in the butt? It would be very complicated to write an iterator for it. But still, you may want to write something like this. If the mouse hit any widgets, and that's any of all these widgets that you get enumerated, and you just check whether one of these widgets got a mouse hit. Okay? So this really would be nice syntax to describe what you want to do, and the same holds true for many other algorithms that you may want to run. So I would like to write this. Now, in order to write this, in order to understand how to do this, we have to understand a little bit more about iteration. The way that C++ does iteration with iterators is somewhat, well, it is one aspect and one way to do iteration, and the other one they're pretty much left out altogether. So what are C++ iterators are doing? They're doing something called external iteration. The consumer is sitting at the bottom of the stack. This is where your regular program runs. And whenever you need a value, you call *it, and this calls a function that produces the value and returns it to you. And so the consumer is really free. Now, the consumer is at the bottom of the stack, right? And it's calling into the producer. Now, what's the consequence of that? You have one contiguous code path with which to consume your elements. You can run your program, and whenever you need a value, you say *it, and you get it back, and your program cannot only be a simple loop, it can be anything. You can do any kind of complicated control flow, and whenever you need a value, you just call into your it. And this is great because you don't have the state that your algorithm is in is pretty much encoded in the instruction pointer, right? You know where you are in your program and what the logical meaning of that is. You can use that where you are to remember what to do next and what you want to do. You can also put things on the stack. You can create any number of local variables. You are free to have any amount of memory on the stack, which is nice. And it will also live across the calls of *it. I mean, naturally, it's a local variable. Now, when you are sitting at the top of the stack, life is much harder. Now, you have a contiguous code path only for each item. You have to implement this operator *. And only for that operator * you can write one function. And then whenever you're done with creating the item, you have to return. So you only have a contiguous code path for that *it implementation. And when you are called again, you kind of have to remember, well, where were I in my iteration and what do I have to do next? And that's what really makes this writing an iterator for this traverse widget so difficult. Where am I in my big tree of widgets? I have to go back there and get the next widget out, and that makes it so hard. It also makes performance worse because you only have the single point of entry, start it, and now I have to do some sort of dynamic dispatch. Where am I going? What am I going to do next? I also can't just put stuff on the stack because, I mean, the stack's gone after I return from my start it, right? If I want more memory, I can go to the heap. That's not very efficient. Well, we can turn this thing on its head, doing something that's called internal iteration. An internal iteration is really what we've done with this traverse widgets. In this case, the producer is sitting at the bottom. The producer is running the actual program. And whenever it has a value to pass on to the consumer, it just calls the consumer. And the consumer is sitting at the top of the stack. So it goes to consumer, gives a value to the producer, gives a value to the consumer, and it returns, and it gives the next value, and so on. Now, in this case, the producer is at the bottom of the stack and has all the advantages of being at the bottom of the stack. And the consumer is at the top of the stack, and it has all the pain that it is to be at the top of the stack. Now, wouldn't the world be great if both could be at the bottom of the stack? That would be fantastic, right? You can do that with coroutines, and I think there was a talk about them yesterday. Now, how does it look like when you're using coroutines? It looks like something like this. It doesn't really compile. It'll look similar to this eventually when they have coroutines. So you say, okay, traverse widgets, and while you're traversing, at some point, you say yield button 1 or yield list box. You're basically passing out a value out of your function. That means you interrupt what you're currently doing, let someone else deal with that object that you just yielded, and when he's done, your control flow just returns to the point where you yielded, and you can keep going. So both are kind of going in lockstep through your code, and one guy is just passing on the items to the other guy, and while they are both executing in unison. Now, that's great. It's very powerful, but it's very expensive. These coroutines come in two flavors. One is a stackful coroutine. There you have any amount of stack. You can call inside the traverse widgets here, for example, you could also call yield. You could yield anywhere. But that has as a consequence that you need a stack, and they are usually implemented as these operating system fibers. And whenever you're doing a yield, you need to do a fiber switch. You need to switch the whole stack, and you need to switch the register context, and you need to do, usually the operating system needs to do it. And the operating system also needs to supply a stack that's usually 1 megabyte of virtual memory, for example, in Windows. The alternative is to do the whole thing stackless. You don't have a real stack in which you yield, which you need to switch. You're saying, okay, the memory that I'm going to occupy is going to be limited, and the compiler can figure this out if you are only yielding in the topmost function, because then you can look into the local variables of the topmost function, and the compiler can find out how much memory do I need. So that limits the problem. But that has as a consequence that you can only yield in the topmost function. Doesn't work here. When you are traversing into your windows, then you can't call yield inside these windows. So that limits what you can actually do with your coroutines. And it's still a bit expensive. You have, when you do this yield and you suspend your execution and resume it later, this resuming is really kind of like a virtual function call, because the place where you yielded is dynamic. It's somewhere in your program, it's some address that you jump to. You also have to save and restore some registers. But in particular, this dynamic jump precludes aggressive inlining, what Chandler talked about in the keynote. You can't do this because you don't really know what to inline. Kind of like in a virtual function call. You can't inline a virtual function call either. So, and that's what you really need. When you're writing iterators, or writing loops with iterators or with ranges, we need aggressive inlining. We need all this stuff to basically go away when it's compiled. You want to be left over with this as if you had a handwritten loop in assembly code. Okay? So, you have to do something else. Actually, with internal iteration, things are not so bad. Okay? It's not supported at all right now by the standard library, but okay, algorithms like find, they don't work with internal iteration because they need to pass out an iterator. We don't have iterators in internal iteration. Binary search doesn't work either because it actually needs random access. We don't have that either. But many other things work. For each works, accumulate works, all of, any of, none of, they all work. They're all fine. They only need internal iteration. You can implement them with no performance penalty with internal iteration. And we don't want to throw this all away. In addition, the adapters that I talked about, that we also use extensively, they can also implement it with internal iteration. You can filter, you can transform. So what we want to do is we want to allow ranges that only support internal iteration. How does it work? Well, imagine you have an any-off algorithm, right, that gets one of these ranges that supports only internal iteration. And you can see the implementation is really trivial, right? Your result is false, and then you enumerate through your range, and this TC enumerate is really just there to hide all the differences between the different types of ranges. It'll turn everything into an internal iteration, and all the actual elements of that range will get passed into the functor. And the functor does what any of hat needs to do, does the OR operation, and then it returns the result. All good? Nah, not quite. Still, any stops when true is encountered, right? It does lazy evaluation. So we need some way to stop generator ranges from passing out the elements. We need to have some sort of protocol to make them stop. And my first idea was, great, this is a prime example for using exceptions, because you are inside your nested function call tree, and you want to jump out in one big jump, and that's really what exceptions do. Well, the problem is they're way too slow. You have to go through the operating system to do exceptions, and that's not going to work. So what do we do? Well, let's introduce an enum that says, do you want to continue or do you want to break? And then the any-off would look like this. You enumerate, and depending on your result, you say, hey, I want to break, or no, I want to continue. I still need to check further elements. What kind of performance penalty does that have? Well, the generator range that implements this can actually elide this check if the functor doesn't return break or continue. It knows in advance at compile time whether the functor that got passed to it will return break or continue, depending on the parameter, of course, that I pass in, but it knows that as well. And when it can ensure that the functor will never return break or continue, will return some other type, then it can elide the check. So you only pay for what you need. Okay, now we are coming to I guess the last thing that I want to show you. And that's, so far we talked about these generator ranges and how they can help when you have these very complicated structures that you want to iterate over. But here I have something much more mundane, much more common. It's a simple concatenation. You have two ranges, and you want to concatenate them end by end. You want to first iterate over the first one, and when you're done with the first one, you iterate over the second one. How can you do that? Well, when you do this with indices, with iterators it's pretty much the same thing, but I'll do it with indices here. It'll look like this. You have, in this case, two different types of indices. One is the index of the first range that you are trying to concatenate, and the second one is of the second range you're trying to concatenate. And they may be of completely different type. One may be a list and the other one a vector. And you're holding references to both of them. And your index is really a variant, that means a union of these two indices. So it'll either contain index 1 or it'll contain index 2, and a variant knows which ones are different from a union. Maybe you know a boost variant, std variant will be now also in the standard. It knows which ones it is containing, whether it contains currently index 1 or index 2. Okay, now let's implement some operations. When you're incrementing the index, okay, what do you need to do? You need to switch. You need to know my current index that I'm at Does it contain index 1? Then I need to increment the index 1 with the help of the range 1 and check whether I reach the end of range 1. Because if I reach the end, I need to step forward to the second range. I need to do the jump to the second range, and that's what's happening here. And when you have index 2, you can simply increment index 2. Well, what if you reach the end of that one? Well, then you are at the end of your range, and you just leave the iterator where it is. It's pointing at the end of the second range. So all good. But you need to branch for each increment. Every time you have to execute the switch, and you have to say, am I currently having index 1, or am I having index 2 for each increment? Kind of ugly. Let's look at the dereference. Same story here, right? I mean, if you're inside range 1 and you want to dereference, you have to dereference something inside range 1. And if you have range 2 currently, you have to dereference range 2. And again, you have to branch. You have to either go there or go there, which is kind of dumb because, I mean, when you're iterating, you really know that you're first iterating over the first range, and then you're iterating over the second range. So this is unnecessarily inefficient. Still, it would be nice to be able to use that simple concat function to concatenate ranges. How can I avoid all these branches? With generators. With generators, the implementation of concat is really, really simple. It's simply this, right? You'll have an operator, it takes a functor, and it enumerates the first range, plugs in the same functor, and then enumerates the second range, and plugs in the same functor. It's kind of like how you would write it in a hand-rolled loop. You would first loop over the first range, then you would loop over the second range, and do the same thing each time. So even iterator-based ranges actually get better performance when you offer a generator interface. Of course, your concat is also going to offer the iterators. That's not an alternative. It's not like it's either iterator or generator. It'll offer both. But if you are having an algorithm that is actually happy with the generator, it will actually use the generator machinery under the hood. And only if you really need the iterators, then it'll go to the iterators or indices. I don't have a slide for it, but with filter, it's actually the same way. When you are filtering a range, then what you usually have to do is you are generating the value, you're getting the value for each filter, and the filter runs, and when you found a position that passes the filter, you stop, and then later on you get the dereference, and you will actually generate the same object again. That's okay if it's just a vector, and you just need to dereference the vector while you're filtering. But if this dereference is rather expensive because you have this long stack afterwards that is going to produce the values and do stuff, then it's actually annoying that the filter is first enumerating the values, including the one that will pass your filter once, and then when you dereference, it'll generate the same value again. And when you do the same thing, when you implement the TC filter with generator ranges, this also goes away. You simply take the iterator, you take the value. When you're happy with the value, you pass it on. If you're not happy with the value, you throw it away. So each item actually just gets generated only once. Okay, and that was it. Now we have all this range stuff. This is the URL of our library. You can download it, play with it, and see how it goes. One last thing, I really hate the range-based for loop. This is a mega accident that this made it into the standard. Why? Because it encourages people to write everything as a for loop. It's again, this for loop is so, oh, we have for loops. Yeah, you write everything as a for loop, and you get this. People write this instead of simply writing this. Thank you very much. Any questions, I think?
How would you compare the internal iterator pattern to the visitor pattern?
Probably very similar. The thing is that the internal iteration is not something that we invented, by no means. I mean, this has been everywhere. The point is just to wrap it into a form that is accessible through the standard library. That's really all there is to it. It's been used everywhere. I mean, but it's so strange that there was no support for it in the standard library, although the pattern is everywhere. I mean.
Thank you.
Concerning the rvalue problem,
yes.
Are there any plans to provide a third way in the stat library, a third?
Say again?
Spite of the action, and you said there are two ways to handle this. You have in a stat library, you have to call action, or in the proposal for the rvalue problem, you have to call some action.
Yeah.
And will there be a third way, so you can actually move the container? Or do you have to write a local variable for yourself?
Well, in the range v3, you have to write it into a local variable in order for it to make it lazy. They basically have only the combination of either you want a view and lazy, or you want a container and you can modify the container eagerly. These are the combinations that they offer. And this is the real problem. Now, whether you name the thing that is generating the container versus the view, the lazy container and the lazy view, whether you name this function the same is again an orthogonal decision. You can make it one way or another. But then you have basically three ways to do this kind of the same. You have eager on containers, you have lazy on containers, and you have lazy and you generate a view. You could have all three, possibly. I didn't find it necessary. For me, two functions were enough, but it's an option, certainly. All right? Oh.
Yeah, concerning that, have you been in contact with Eric Niebler about that? So what's his take on this? So is he going to add that, or?
We actually had papers at the C++ standard committee meeting describing the generator concept, and from personal interaction with him on news groups and also talking to him directly, I know that his problem with doing the view filter, or why he's so adamant about the view filter, is that really the concern that one would generate a range and the other one would generate a container, and they behave very differently. And that's what they're really afraid of, kind of. That's what they don't want. Again, I understand that, and well, I understand this concern. It wasn't a problem in our code. The other thing that I also talked to Eric about, and maybe that was rather a didn't get to it yet kind of thing, this advantage of using indices. The thing with the indices is really you can leave it, and this is kind of how the direction it's currently going to. You can leave it as an implementational detail. You can say, well, every compiler vendor, library vendor is free to create their adapters with these indices under the hood, and it'll just make them more efficient. That's not quite the whole story, because you want people to be able to create their own adapters. And this whole index idea only really works when you support the indices everywhere. Because when you have this stack, you need to be able to play this index going down game all the way to the back to the vector. If you're getting stuck after 2 steps, then really there's no point doing it. So we really need some sort of publicly documented interface, how we do this index stuff. And this, in my point of view, needs to go into the standard eventually, should go into the standard. Nothing that's currently in the standard precludes us from adding this later. So that's good. And what's really crucial is that and that was one reaction we got from the work that we did, is they changed, or they added this requirement that the iterators must not outlive the range. That was a crucial restriction to put in, because if they had not required this, then we really would have been lost. We wouldn't be able to implement this stuff efficiently anymore.
Thanks.
Again, with the filter, you mentioned that it's not a problem in your code, but how do you know that? Because you might get the wrong behavior, non-lazy behavior, without noticing it.
Okay, well, I mean, we do code reviews. So we basically have lots of developers who are maybe not as experienced write code, and then more experienced people look at the code, and so you get kind of a feeling of what kind of mistakes happen. Did we catch all of them? No. Our software has bugs just like any other software, but there is this mutual checking, and you kind of get a feeling of what's causing problems, what's causing misunderstandings when people write code. This is good about having an organization of maybe 15 programmers who actually write with this code with this stuff. That it's not just one guy who actually thought it all up and is now intimately familiar with it, but we actually distribute it and we say, okay, no, you must write your loops and your things with ranges and try it out and see how it works for you, and then we'll see what kind of mistakes happen if a newbie starts working with this stuff. So that's my experience, where I got the experience from.
Okay, thanks.
Hello. My question is, did you profile it against containers that are not cheap to move? For example, std array or strings which exploits small string optimization, something like that?
I didn't. You mean the R-value stuff?
Yeah.
Yeah, so actually the R-value, so no, I did not, and obviously it would be expensive. If this thing is a huge array, then you do have a problem. Usually containers are not. That's my answer. This idea of moving the R values in also actually goes back to an idea from Google. They do the same thing with basic. They have a basic string view class that they also want to get into the standard, and it behaves like this. So there is little alternatives you have. Whenever you have some sort of thing that holds a reference and it gets an R value, what are you going to do? So what you're doing is you're moving it in. And yeah, is it expensive with arrays that are large? Yeah, it is.
Okay, thank you.
But the alternative is a dangling pointer, which you don't want to have. So. All right. Thank you very much.